Good afternoon, everyone. This is our presentation, LiDAR-based home mapping, using the OSLRF 01 and Arduino to generate floor plans. My name is Soren Patel.
My name is Aditya Sridhar.
I'm Lyndon Shree.
I'm Eric Ward.
And I'm Eric Dahl.
So to give a brief overview of our presentation today, we'll be starting off with the introduction and background, then talking through our design and construction phase, discussing our testing and results, and then conclusions, summarizing ideas, and future ambitions.
So the goal of this project was to use a laser-based distance sensor, shown on the right and the left, in order to generate a floor plan. By rotating the sensor through small angles and taking a distance at incremental angles, we could generate a polar graph which would resemble a floor plan similar to the one on the right. The way that the LiDAR sensor calculates distance is by measuring the time of flight of a laser, which it emitted from one lens, and then the amount of time it takes for it to reflect from a surface and back at the desired distance. The time of flight of the laser is directly proportional to the distance away from the object.
Okay, so in the modern world, ultrasonic sensors, as you see on the top right, are fairly good at measuring distances, but they are not very accurate when it comes to measuring large distances. So a better solution that's getting cheaper and more affordable day by day, a solution that is more efficient than the ultrasonic sensor is a LiDAR, which stands for light detection and ranging. The LiDAR uses laser pulses to measure distances up to great lengths. As in the tile LiDAR-based home mapping, we use the LiDAR to map out a room 360 degrees, as you can see in the bottom right. Some of the future applications of the LiDAR include mapping out structurally unsound buildings, as well as finding solutions to antiquated or non-existent floor plans.
So before we talk about the specific details of our project, I'm going to go into some of the major components that make it up. So one of the things we used was the Arduino Uno, which is a microcontroller board. This board has 6 analog input pins, each of which are connected to an ADC, or an analog to digital converter. Each ADC has 10-bit resolution, which means that an increase in 1 in a binary output of the ADC corresponds to an increase in 4.9 millivolts on the analog input pin. Additionally, Arduino Uno has 14 digital I/O pins, which can read, write, and perform pulse modulation, or PWM. So PWM is a technique for getting an analog output using a digital pin, and this is done by modifying the pulse width of the pulses from the digital pin. Finally, the Arduino Uno is programmed using a language similar to C++.
Another big part of our hardware was the Futaba S3003 standard servo. There are 2 main types of servos, standard and continuous. A standard servo moves in angular increments and can move from 0 to 180 degrees, while on the other hand, a continuous servo can move freely as many degrees as needed and is based off of time and speed. For this project, we decided to use a standard servo because the LiDAR sensor needed to know where it was in the room when it mapped. Another reason we chose this servo is because the Arduino Uno can output a voltage of 5 volts. This servo can operate from 4.8 volts to 6 volts, making it ideal for our purposes.
So the main component of our project was the open source laser rangefinder, which is the first affordable LiDAR sensor available to hobbyists and students. The sensor emits a laser pulse every 122 nanoseconds, which is actually too fast for a microcontroller such as the Arduino to be able to sample to any significant value. For this purpose, there's a circuit within the sensor which expands the timebase. Since this is a variadic timebase expansion, one of the digital outputs is the synchronization signal, which is a square wave which indicates the amount of time each measurement is taking. The falling edge of the square wave represents the end of the previous measurement and the beginning of the next measurement. The 0 analog output represents the power being emitted by the laser, while the return analog output represents the power in the detector.
So after choosing our components, we moved on to the design and construction phase of our project. To begin, we connected the Arduino to the LiDAR. Since the return and 0 signals are analog output signals, they were connected to analog pins on the Arduino. The sync signal was a digital output, so it was connected to a digital pin on the Arduino. The OSLRF also includes an analog input pin, which is called control, and it can be used to control the time-base according to the types of measurements we want. A 12-volt wall power supply was used rather than the Arduino because the Arduino can only output 5.5 volts, 5 volts and 3.3 volts. And then we moved on to the testing phase of our device. So as you can see, the values we read in when we pointed the laser at a wall roughly 2 meters away, the return and 0 signals shown in blue and green occurred once per sync period, indicating that the laser projection and detection were correct. The sync signal shown in red is periodic, indicating that the time base was working correctly. Each sync period corresponds to 18.33 meters. Therefore, the ratio of the two peaks in a period to the actual sync period can be used to calculate the distance.
Okay, so the servo library in the Arduino programming language makes it easy to control the servo using Arduino boards. In this case, we have the Arduino Uno, which is the one we use. The software used to control the servo, as you can see here, is the servo.h. Additionally, to measure, instead of using integral degree measurements, we use duty cycles because it makes the measurements more precise.
So another big component of our project was the base design. The base design was composed of a couple different parts, including the Arduino housing, the servo mount, and the LiDAR mount. As you can see here, this was the Arduino housing. We needed to make sure that it was built to specific specifications to make sure that the Arduino did not move around too much. If it did move around too much, our electrical components could become damaged or wires could become loose. We also built some other parts, as you can see, and then they are assembled on the right-hand side in a program called Autodesk Inventor. We also took an aesthetic appeal. Our project is called LiDAR-based home mapping, so then we thought it would be appropriate to make the design in the shape of a house. As we said before, the gearing system, the standard servo can only operate from 0 to 180 degrees, but we need a 360-degree rotation for our project. So in order to accomplish this 360-degree rotation, we set up a gearing system. The way this gearing system works is there's a big gear and a small gear with a gear ratio of 2 to 1. What that means is that the big gear has 2 times the amount of teeth as the small gear. So the big gear, as modeled in the two pictures, on the left-hand side in the 3D modeling space and on the right-hand side in 3D printed, the big gear will have twice the amount of teeth as the small one, and the big gear will be attached to the servo with the small gear attached to the LiDAR. So half the rotation of the big gear will result in a full rotation of the LiDAR.
Once we finished prototyping the electrical components and designing the mechanical structure, the next step was writing the final software application. The LiDAR sensor and motor modules each have their own respective files, which are interfaced with the main file, Room Scanner. The Room Scanner program works by incrementing the motor by a small angle and then measuring a distance through the LiDAR. It then outputs this polar coordinate over a serial connection to the plotting computer. On the plotting computer, we are running a program called Octave, which is an open source version of MATLAB, a program that allows you to do visualization and processing of large data sets. The Octave script we have running listens for a serial each polar coordinate on the serial input stream and then plots it in real time, making debugging and error detection easier. Once the Arduino finishes its sweep of the room, it sends an exit signal to the script, which tells it to save the points to a file and exit.
So here on the slide, you can see some pictures of the finished components we have. So on the left, you can see a prototype of our mapping device. As you can see, the base is not 3D printed. It's actually assembled using Legos, because at the time, our print did not come in and we needed to get results, so that's what we used. And then on the right, you can see our assembled 3D printed base, but without the components inside.
So I'm going to begin describing the testing phase of our project. And the first component of our testing phase is the calibration. To calibrate the LiDAR, a set of distances from 1 to 9 meters in 0.2 meter increments were marked on a line on the floor of a large room. The OSLRF was attached to one end of this line, and white poster paper was held at various increments along the line from the OSLRF, and distance measurements were taken. The program calculated the ratio of the laser time of flight, as you can see on the graph, to the actual distance, and then that ratio was plotted on the graph as a function of the actual distance. The line of best fit, as you can see on there, showed the proportion of the ratio to the actual distance to be constant regardless of what distance you used. The proportionality constant, as represented by the slope of this line, it turned out to be 18.22, which is very close to 18.33, the actual value we're supposed to get. But that's really good. And the R-squared value is 0.999, which shows an almost perfect correlation.
So another thing we had to consider was the trade-off between accuracy and time base. So what the time base is the amount of time the sensor allocates to take the distance measurement. And obviously, the longer the time base, the more accurate these measurements are. However, at the same time, we want to map the room as quickly as possible. So we set up an experiment. We took a controlled distance and measured it using several different time bases, and we took 10 measurements using each time base. Then we plotted the data on this graph as shown. So as the graph shows, the accuracy does increase as the time-based signal increases, up to a point of about 2.25 volts, at which point the accuracy changes are more negligible. Despite this, we decided to use 3.3 volts on a control pin just to ensure that we're getting the largest possible time base at all times.
So with the fully functional servo and sensor circuit, we began mapping a room. In the trial shown here, we mapped a room that was 2.87 meters squared. As you can see, the walls in the room were not mapped as precisely as we'd like because we were using a prototype. In figure 17, you see the actual room in a different orientation and the area that it covered. Regardless of the results, we proved that the LiDAR can be used for home now.
So we've been working on this project for about 4 weeks now, and we're pretty proud of what we got. We're pretty happy with what we've accomplished. So one of the major goals was to create a map of the room, and we were able to achieve that. We were able to generate a rough map. Additionally, this project was actually really cheap. It cost less than $200 to make, making this easily reproducible by other hobbyists to use for their own needs.
LiDAR has potential for the future. The device we created could be adapted for 3D mapping. If we mounted it on a servo that allowed for vertical motion, we could plot the points read in a 3D space rather than a 2D space. As previously mentioned, it could also be used in home mapping, and further projections suggest that it could replace ultrasonic sensors in robotics.
So we would like to thank our mentors from Lockheed Martin, engineers Ryan Flynn, Joe Grossman, Eddie Kahn, and Nick Papasso, for providing invaluable technical support and guidance throughout the course of this project.
We would also like to thank our amazing RTA Rowan Kanj for supporting us along the way, providing us with any resources that we desired, and cooperating and collaborating with us during the course of this wonderful project.
We would also like to thank Dr. Eileen Rosen and Associate Director Jean-Patrick Antoine for making this program possible.
Further, we'd like to thank our sponsors, Rutgers University, New Jersey Resources, Silverline, and South Jersey Industries.
And also Novo Nordisk, Rutgers School of Engineering, Lockheed Martin, and the state of New Jersey. Thank you for your time. Are there any questions?
How long did it take your device to map that room?
Depends on the accuracy you desire. The one we showed, the map we showed, I believe that took about 5 minutes.
Right.
Yeah, can you go back to the graph? Can you explain what's going on here? Sorry.
Okay, so what happened was we took control distance and we measured it using various time bases. So the time bases are applied on x-axis, and we took 10 measurements using each time base. So like, if for example, like 0.75 volts, we took 10 measurements, and the readings, the distances are plotted. And then these readings show us that like for a lower time base, the readings are more spread out, as you can see for like lower voltages. And the higher voltages, the distances sort of come to a point.
So if the device were perfectly accurate at all voltages, these would be vertical lines, right?
It would be one horizontal line
It
across.
would be one horizontal line across. Okay.
Anyone else?
So what kind of laser beam you are using? What's the wavelength?
I don't know off the top of my head.
Yeah, we're not quite sure exactly what wavelength it is.
It's kind of red, right?
I believe it's a pro.
Okay. If there aren't any more questions, thank you.